Okay, let's start. It's time now. Let's start today's session. So, good afternoon, everyone. This is the interactive session 6th. As you all know, and for new people, this session happens every Saturday from 3 p.m. to 5 p.m. and it's recorded as well, so you can find it in the Google Drive link provided. This is the session for NPTEL course Experimental Physics 1, which is being taken by Professor Amal Kumar Das from IIT Kharagpur, and I am Rinalini, PMRF Research Scholar from School of Physics, University of Hyderabad, and I will help you in doing the assignments for this course. Moving forward, okay, a quick recap. So last week, that is in the 5th interactive session, we understood the theory and the theory for determination of Young's modulus of a material. For this was our experiment 1. We understood the theory, the procedure, and did questions based on this particular experiment. We understood this procedure, which was flexure method. After this, we did understood the second experiment, which was determination of spring constant of a material, and did questions based on this as well. Then our third experiment, that we understood only the theory, was determination of moment of inertia of a flywheel. So in last class we had discussed what is moment of inertia, its significance, and how to calculate moment of inertia for different bodies corresponding to different axes of rotations. Now in this class, in today's interactive session, we'll start with quick review of what's the procedure for this particular experiment, and then of course we'll continue with solving the problems based on it. So as you have already seen in the lecture, determination of moment of inertia of a flywheel, this is the typical setup that we use for this experiment. So here, this wheel thing that you see is what we are calling a flywheel. This wheel with this is called axle, as you can see here. This is the axle, this rod going through this wheel. This whole thing together, this flywheel and this axle, is called the flywheel. Sorry, this wheel and this axle is together called the flywheel that we use for this experiment, and whose moment of inertia we want to find out. So this flywheel is set up at a distance from the floor, and what we do is we tie a mass. Here is that mass. We tie this mass. This is the thread. We tie this thread along this, right? So if this is the wheel, this is the wheel, this is the axle, and we hang this is straight, and there is a mass, and how we are not pasting it, or we are not putting a knot here, we are just turning it on this axle. As you must have already seen in the videos, the professor has already very clearly demonstrated this experiment. We are just revising it here. So this is the number of turns, and these are, the thread has been turned on the axle, and this is how it hangs here, and this is the height. So height from here, from the mass when it's hanging to the floor, we take its h, right? We take this as h, and the radius of the axle we measure. From there we get the r. This is the h, and okay, how do we get the working formula for this experiment? Let's focus on that. So so this is our wheel, this is the axle, and the mass is hanging here. This is the floor, and this is the height. You can either take it from center of mass of body or from here. Whatever you're taking, just keep it same. So here we know that when the body is at a height from the floor, there will be some potential energy stored in the body, right? It is at some height, means that there will be some potential energy corresponding to this body which has mass m. That potential energy will be mgh. Right now only this energy is there in the picture, but as soon as we'll leave this mass, because it's not tied, so it will start coming down and this turns will start opening. Thus when it starts coming down, h is decreasing, h will decrease, that means the potential energy will decrease. And since we know energy can neither be created nor destroyed, we know this conservation of energy law. This means that potential energy will not get destroyed, but it will convert into something else. That something else will be the kinetic energy. So when this mass starts coming down, that means its potential energy starts decreasing. That energy gets transferred to this flywheel, and this flywheel as a result starts rotating. So the energy goes into the kinetic energy of the flywheel. The kinetic energy of flywheel, we know this, we had discussed last time. This is half I omega square. This this is moment of inertia, this is angular acceleration, angular velocity, and this is the kinetic energy of this flywheel when it's rotating. Also this mass is moving, right? So there is kinetic energy associated with this mass also. That will be half mv square. So all this potential energy is getting converted into the kinetic energy of flywheel and the kinetic energy of the body. Also there is one more way in which this energy is getting spent. That is the the friction energy. There is a system, like you can see here. There is a setup here. There is ball bearing on which this axle or this rod is moving. So there is some friction there, and we'll understand in a few minutes what is the role of that energy, that frictional energy. But we need to understand that there is some energy out of this potential energy that is getting spent in form of frictional energy also, and that will depend on this number of turns, and this F we are defining here, which is the work done against friction per unit turn. So this is the equation of motion we'll get. This is just the equation that we get. This is the situation when the mass just leaves, just these turns completely open, and this mass detaches from this flywheel. At that time, this is the equation in picture. After that, when the mass has already detached, let's call it equation 1. When the mass has already detached from here, all the turns have opened, and that time still the flywheel will keep on rotating because it has got some energy. It will still keep on moving, and so our second equation will be, it will still keep on moving, half I omega square. But how long it will move? We know it will not keep on moving forever. It will stop after some time. And what is the reason? That happens because of friction. Because there is friction between the ball bearings and this axle of this flywheel, thus it will eventually come to halt, and that will depend on, again, number of turns we are counting after the mass detaches. So number of turns the flywheel takes, and F is again the same frictional constant. So this is the this kinetic energy will be equal to this frictional energy. So this motion will come to a halt because of this frictional energy. From equation 1 and 2, I'm not going to derive it because the professor has already done this, as you have seen in the lecture. So what I just want to tell is, this is the basis for getting the working formula, and the working formula from these equation 1 and 2, we find out that moment of inertia that we obtain from these two equations, the formula is I is equal to m 2gh omega divided by omega square. If you have any doubt in this, you can ask. Otherwise, there is no need to repeat it because it's already there in the video lectures. Minus r square divided by 1 plus n1 by n2, where omega is 4 pi n2 divided by time. And you know how the experiment has to be done, right? Like we need to take different, either take different mass, or we need to basically we can change here the mass, also the height, and we can keep on repeating this experiment. And we need to note down the number of turns, we need to note down the time after the mass detaches from the axle, and using those parameters we will finally calculate the moment of inertia, and we will take average for getting a better value for this experiment. So this is the working formula for our experiment. So moving on finally with our problems. Here is the first problem based on the concept of moment of inertia. So the question is, a body of mass m is rolling without slipping. The radius of gyration of the body about an axis passing through its center of mass is k. If the radius of body is r, then the ratio of translational kinetic energy to rotational kinetic energy is. So we have been asked that a body of mass m. So we have not been told what is the shape of the body. So the shape is not told. So I mean, just imagine any shape of the body. It's just a body of mass m which is rolling. It may be flat surface or maybe slope surface. That also we have not been told. It doesn't matter. But anyway, this is rolling. Means this is rolling without slipping. Most probably, I think it's like this. So that the body is here and it's rolling, and as well as it's doing some translation also, right? It will keep on rolling and come down. So we have been asked to calculate the ratio of translational kinetic energy to rotational kinetic energy. So we know that kinetic energy I am denoting with Ke, translational energy. So we know that translational kinetic energy is given by half mv square, and rotational kinetic energy is given by half I omega square. Here we have been given radius of gyration. Since we know that moment of inertia and the relation between the radius of gyration and moment of inertia is like this, that I is mk square. Okay, so when we take the ratio of these two, in short I'll write T and R, KET and KER, then we'll get half mv square divided by half. If I put the value of I from here, then I'll get half mk square and omega square. So half cancelled, cancelled, we'll be left with v square divided by k square omega square. Now since we know that v is equal, this is the relation between linear velocity and angular velocity. From this we'll get omega is v by r. Substituting this again here, we'll get, this will remain, numerator will remain as it is, radius of gyration, this is omega is v by r. That means dividing by v by r means r square by v square. So again this will be cancelled and we will be left with r square by k square. So our answer will be D. This is the correct answer. Okay, so now next question. So next question is, a solid body of mass m slides down an inclined plane. So there is an inclined plane and there is a solid body. Again, the shape has not been told. So okay, some kind of body this is of mass m. It slides down an inclined plane and reaches the bottom with velocity v. Okay, when it reaches the bottom, its velocity is v. If disk of same mass rolls down the same inclined plane. Okay. Next situation is, if on the same inclined plane we have this time a disk. We have a solid disk. This is like complete solid disk. It's rolling down and same mass m. What will be its velocity on reaching the bottom? So first we'll see what is the energy here for this first body. So for the first body, and this is the second body, which is a circular disk. For first body, the energy will be after it reaches here. Okay. So what we need to do is, when it was at top, it had only potential energy. Okay. And when say some height of the inclined plane is some h, and when it reaches the bottom, all its potential energy would have converted to this kinetic energy, right? That let's call half mv square. And for second equation, the same thing, but here now it will have now it will have its equation of motion will be just it will have rotational as well as kinetic energy. So because for the first body it was said that it slides down, means it's not rolling. This body is not rolling, it's just sliding down, so it's only translating. Whereas for the second body, that is this disk, we have been told that it rolls down the inclined plane. So now this body is rotating, it's rotating also, and it's covering a distance also. So here it's only translational motion, here it's rotational as well as translational motion. So for second body, the equation will be half I omega square plus half m. Mass is same anyway, but let's height is same, mass is same, that is fine, but let's call this v. Okay, I'll call this v1, and no, we have been given the first v, so we'll just keep it as v, but we'll call this, let's call this 2, because this is different and we need to find out the value of this, and this will be v2 square. Now from comparing equation 1 and 2, right, I can substitute the value of mgh from equation 1 here. So putting 1 in 2, so equation 2 becomes half mv squared is equal to half, and here I can put the value of I also actually. So I mean moment of inertia for the second body, this is circular disk, right? So this we have kept for reference. So for a circular disk, you can see circular disk, and when the center of mass is perpendicular and passing through the plane, the moment of inertia value is half mr square. So here also the body is rolling and the center of mass, the axis of rotation is through the center, right? So the same formula we'll use. The value here will be half m r square. So it will be mr square, and omega will be what? We know v is equal to r omega, right? And here it's v2 and some, I mean, okay, maybe we can just let it be. V is equal to r omega, so omega will be v by r, or I should put 2 to avoid some confusion. Yeah, okay. Wait, let me erase this. We'll make it 2 so that we don't get confused, because we are doing it for the second body actually. So v2 will be r2 omega 2, so omega 2 will be v2 by r2. So this formula will also become this mr square, means this r is corresponding to the second body, times omega square. Oh wait, this half is here. Now moment of inertia is half mr2 square, so there is one more half when I'll put the value of moment of inertia here. Now for omega square means this omega square means v2 square divided by r2 square plus half mv2 square. So you can see r2 square cancelled, we will be left with 1 by 4 mv2 square plus half mv2 square. So from, okay, let me repeat it again, half mv square, so half and half will be cancelled, we will be left with this, m will be cancelled, so what we are left with is v square is half v2 square plus v2 square. So this half plus 1 means 3 by 2 v2 square. Now the question was, what is the velocity of this second body on reaching the bottom? And the options are in these. V is velocity of the first body, that means we are supposed to find out the velocity of second body in terms of velocity of the first body. So from this equation we'll find out, so this will be 2v square divided by 3, right, is equal to v2 square. When we'll remove the square, we'll be left with this v2 will be taking square root here, right? So it will be root 2 by root 3, and it will be, yeah, so it will be root 2 by root 3, and this will be v. So our final answer will be this, root 2v by root 3. This is the correct answer for this case. What we had to keep in mind was that the first body, it was given it slides down, so only translational part we'll write, and for the second body it was rolling down, so there will be rotational kinetic energy as well as translational kinetic energy. Okay, and the next question, this is just, we'll keep on coming to here when we'll be solving questions and we need these values. Okay, so this is the question. A solid sphere and a hollow sphere made of two different metals but of the same mass and they should be same outer radius are given to you. So we have a solid sphere, and a hollow sphere. Immediately what we should come in our mind is that their moment of inertia is actually different, but okay, anyways, let's see what's the question. So they are made up of two different metals, but they have same mass, so their mass is same, let's call it m, and same outer radius, their radius is same, let's call it r, are given. Which one of the following methods will be suitable for identifying them? We want to identify means we want to identify that we have been given two mass and we cannot hold it or something. We just have it in front of us, and we need to find some suitable method based on which we can tell that which sphere is solid and which sphere is hollow. So identify means we need to identify which one is solid, which one is hollow. So we have been given A, B, C, D, these four options, and we need to tell which one is the correct way to determine this thing, that if which one is solid, which one is hollow. So the first option is arrange two simple pendulums of equal length with the hollow sphere and the solid sphere as bobs and compare their period of oscillation. So will this simple pendulum method will work or not? So we, okay, where is my cursor? Yeah. So for A, we know that for a pendulum, and if you time period of oscillation, right? So we know time period is actually 2 pi under root L by G or K by M. This is also, or no, for this it's okay. Or we can also write, yeah, K by M, that's fine. So it doesn't uh, even when we take it in this form, this is for spring actually. So there is no relation here with the radius. I mean, anyway, the radius is same, mass is same. So it will not distinguish between the, just determining the time period will not help us, because it doesn't distinguish between the solid or the hollow sphere, because the radius is same and the mass is same. So this will not help us. B is supply equal charge to them and compare the electric potential on them. Okay, so if we'll try by supplying equal charge to them, and then by putting comparing the electric potential on them, this experiment will also not help, because when we supply charge, the charge is deposited, the charge is collected on the body, right? If I'm giving positive, it will go on the surface. So even if it's solid, even if it's hollow, the charge will be at the outer surface. So it will also not help us distinguish the solid and hollow sphere. The C option is allow them to fall freely under gravity. Fall freely under gravity from the same height and compare their time of fall. Well, this experiment will also not help, since if they are falling freely under gravity, we know G, right? G is acceleration due to gravity, and acceleration due to gravity when the body is freely falling. When body is freely falling, there is no other force on it, and the value of G is always same. So this will also not help us in comparing. The fourth option is allow them to roll down from top of the same inclined plane and compare the time taken to reach the bottom of the incline. So as we are doing the questions on moment of inertia, so as soon as it's mentioned then one is solid, another is a hollow sphere, it should come to our mind that moment of inertia, we don't know about, I mean, this time period of pendulum and charge and freely falling body, these are different things, but we know one thing, that moment of inertia comes into picture, and we know that moment of inertia for solid sphere and hollow sphere is different, right? We can see from here, moment of inertia for solid sphere is 2 by 5 mr square, and for hollow sphere it's 2 by 3 mr square. So for solid sphere, moment of inertia is 2 by 5, m and r are same. Moment of inertia for, okay, let me call it is, let's call hollow, so IH, here the value is 2 by 3 mr square. Okay, we can see in the diameter, here it's 5, here it's 3. So what does this show? This show that moment of inertia of moment of inertia of hollow sphere is more than moment of inertia of solid sphere, right? Because it's 3 is in diameter here higher value in diameter means this overall value is smaller. So moment of inertia of hollow sphere is more than moment of inertia of solid sphere. What does this mean? This means that there is more inertia in this body, right? There is more inertia in this body, so it will take more time for this body to roll. so it will reach the end later, because we know moment of inertia is the analog of mass. When we talk about body of mass and moving in translation motion, right, we had discussed this thing. When a mass is going moving in a straight line, there is it has mass m, and the linear motion, linear velocity is v, and it's analog in rotational motion, that if around an axis the same mass is rotating, then here comes the analog of it, which is rotating, thus comes analog of mass, which is moment of inertia, and for v it comes omega. So basically the higher the mass, as we know in linear motion, if you are trying to push this object and it is heavy, means you need to put more energy to move it. Same way in rotation, if its moment of inertia is high, means there is more energy required to move it. So what will happen when we let it roll down from top of inclined plane? In top of inclined plane, imagine in parallel we have kept solid and hollow and solid sphere, and they are on the same position and they are rolling down. So because moment of inertia of hollow sphere is more, so first the solid sphere will reach and then the hollow sphere will reach. So based on this, we will be able to tell that which one is hollow and which one is solid without touching it or weighing it, just by observing it. So B is the correct answer. That is, the way to distinguish the hollow and solid sphere in this particular question would be taking the concept of moment of inertia. Okay, now the next question is so the question is, the moment of inertia of a body about a given axis is 2 kg meter square. So we have been given value of moment of inertia, which is 2 kg meter square. Initially the body is at rest. In order to produce a rotational kinetic energy of 40,000 joules, an angular acceleration of 5 radian per second square must be applied about that axis for duration of. So the question is basically this, that we have been given moment of inertia value, and we have been given that body is at rest initially, and in order to produce a rotational kinetic energy of this at angular acceleration of 5 radian per second square, if we want to produce rotational kinetic energy of this value, then how much long we need to give it angular acceleration of 5 radian per second square. So rotational kinetic energy, the formula we know, right? Rotational kinetic energy is given by half I omega square, and this value we have been already given, which is 40,000 joules, and I value is also given, so I'll substitute that here, so it will be 2, and omega, okay, so wait. So this is we have been given angular acceleration, that means alpha we have been given 5 radian per second square, and in the formula we have omega, which is angular velocity. So first we'll solve this. From this, the value of angular velocity will be, we'll take root of this, right? So it will be 200 radian per second. Value will be this. Now, since we know that alpha is time derivative of angular velocity, this means d omega will be alpha dt. We'll integrate and we'll get omega is equal to alpha t. Omega we have, which is 200, alpha we have 5, we need to find out t, which is what asked in the question. Thus the time will be, this will be, 40, this will be 40 seconds. So with this angular acceleration and this for this kinetic energy, the time is 40 seconds. We need to apply for this angular acceleration for 40 seconds, to achieve 40,000 joule of rotational kinetic energy. So our answer is C option. This is the correct answer. Okay. Now the next question. A flywheel rotates with angular velocity which is given by this expression. Find its angular acceleration at t is equal to 1 second. So again, using the relation between angular acceleration and angular velocity, since we know alpha is d omega by dt and omega is this, that means we need to take time derivative of this 10t minus 5t square radian per second. Taking derivative of this will be this, and here 2t, right? This means 10 minus 10t. Now angular acceleration we need to find out at t is equal to 1. So angular acceleration at t is equal to 1 will be, so when we took derivative we got this expression, right? So we need to find out the value of this at t is equal to 1. So when we'll substitute t is equal to 1 in this expression, we'll get alpha is equal to 10 minus 10. It will be 0. Yeah, it will be 0. Okay, so angular acceleration at first second or at t is equal to 1 second will be 0. This is the answer. And now the next question. The angular velocity of a rotating wheel changes from 30 rpm to 60 rpm in 5 complete rotations of the wheel. Calculate the angular acceleration of the wheel. Okay, so angular velocity, which we denote by omega, so changes from 30 rpm to 60 rpm. So let's call this initial angular velocity and final angular velocity will be 60 rpm. So I am denoting omega I means initial angular velocity, which is given by 30 rpm, and then final angular velocity will be which is given 60 rpm. Then if you remember equation of motions, for linear motion we have this 3 equation of motion, right? The third one is v square minus u square is equal to 2as. This is the final velocity, this is initial velocity, this is linear acceleration, this is the distance. So this is the equation of motion, third equation of motion for when a body is in linear motion. When we'll put it into rotational, for rotational motion, this will change to, this is final, right? Final velocity minus initial velocity, and angular acceleration we denote by alpha, and s distance. So rotation is there, that means when we talk about rotation corresponding to an axis, a body is here initially, then it rotates and reaches here. So here the distance actually is this theta, it's covering this angle, so this is this theta. Okay, so for you when I'll put the value of omega I, omega f here and express it in form of in terms of alpha, I want to find out. So alpha will be omega this minus initial this and divided by 2 theta. Now we need to keep in mind one more thing, that is we know that like one circle or face of clock or anything, when it completes one rotation, that means 360 degree, right? Or in terms of radian we call it 2 pi. Correct? Pi is 180 degree, 2 pi is 360 degree. So one rotation means 2 pi. 2 pi is one rotation. That means this omega I, which means 30 rotations per minute. First I would like to convert this minute to second, because we like to deal with same unit, and Here our answer is in second. So let's convert this also into second. So 30 rotations per minute. If I, okay, 30 rotations per minute means 1 minute is 60 seconds. So when I will divide by 60, it will become rotations per second. This will be half. That means half rotation per second. Now we know for one rotation means 2 pi radian distance will be covered. So half rotation means omega I means half rotation per second, which is equal to one rotation is 2 pi, so half rotation is pi, right? This is, yeah, pi radian per second. So omega final will be, it's 60 rpm. That means double of omega I. That means it will be 2 pi, right? Radian per second will be the angular velocity in terms of this pi angle if we express. So putting this here, omega f is 2 pi square of this and square of this pi square divided by 2. Now this theta is what we have been given. How much distance it will cover? The angle it will cover, 5 complete rotation. Again, one rotation is 2 pi, that means 5 complete rotation. 5 complete rotation, theta we have been given, it is 5 rotations. 5 rotations. And one rotation is 2 pi means 5 rotation is 5 times 2 pi radian it will cover. That means 10 pi. 10 pi. Again solving it, this will be 4 pi square minus pi square divided by 20 pi. So this will get cancelled. 4 pi minus pi means 3 pi divided by 20. So this is our answer. Angular acceleration will be 3 pi by 20, and putting the SI unit, it will be radian per second square. So our answer is 3 pi by 20 radian per second square. This is the correct answer. Okay. The next question is, the diameter of a disc is 10 centimeter and mass is 20 gram. There is a disc. Okay, I mean, you can imagine it like this also. I was just putting from the front, it will look like this, so that's fine. And the diameter, okay, we have been given diameter. We have been given diameter is 10 centimeter. Its mass is 20 gram. Calculates its total mechanical energy when it rolls along a plane surface. So there is a plane surface and it's rolling. Rolling means it's rolling on its circumference, right? You cannot roll any other way. So it's rolling like this on a plane surface with velocity 4 centimeter per second. 4 centimeter per second. Now we have to calculate total mechanical energy. So it's rolling means there will be rotational energy as well as translational energy. So what will be the energy? The energy I am denoting with E. It will be rotational plus kinetic. Rotational will be half I omega square and kinetic will be half mv square. Now again, for this disc, we have just been told it's a disc of diameter this. We have not been told it's hollow or something, so we are considering it solid. So moment of inertia for solid disc, moment of inertia for solid disc is half mr square. Okay. Where so D is 10 centimeter, that means R will be 5 centimeter. So here this is in CGS. This is CGS unit, it is not SI, but the answer is also in CGS, so we will not convert it into meters or kg. We will just keep it as it is because our answer is also in CGS unit, right? because in SI unit the energy of SI unit of energy is joule, but erg is the unit for in CGS system, centimeter, gram, second there. So we will keep it as it is. So half m r square, r is 5 centimeter, and omega, again using the relation v is equal to r omega, implies omega is v over r. So substituting these things here, we will get half, moment of inertia value is half mr square times omega. Omega is v by r, and we need to take square of this plus this kinetic energy, which is half mv square. This is separate. So yeah, this will be, let's calculate this, it will be 1 by 4 mr square v square by r square, again this r square get cancel, plus half mv square. So the value of this, basically this will be 3 by 4 mv square. Now substituting the value of v and r that we have been given, so it will be, and we have also been given the mass, right? Mass is 20 gram and v is 4 centimeter per second. That is also correct. Oh, we make some mistake. Okay, this is v square, means 4 square. Let me correct this. Sure, like this. Yeah. So it will be 4 square. So this 4 will cancel 1, 4. We will be left with 3 times 20 times 4. That will be 240. 240 erg, because the energy will be in, yeah, this is the energy that we are calculating, and its CGS unit, it is erg. So the correct answer is 240 erg. And we have one more question. This question says a solid cylinder of mass m. So let me draw here. A solid cylinder of mass m. We have been told, keep in mind that it's solid. It's a solid cylinder of mass m and radius capital R is rolling down an inclined plane. Okay, again this is a question of, so whenever I am drawing it, actually just keep in mind, of course it is some sort of this kind of inclined plane, means it has slope and it's rolling down here again on circumference. From the front it looks like this. This is the solid cylinder that is rolling down. Rolling down means rotational energy and translational kinetic energy, because it's moving, right? It's rotating as well as translating. And the inclined plane, the height of this plane is h without slipping. Okay, the speed of center of mass when cylinder reaches the bottom of the plane. So when this cylinder reaches the bottom of plane here, the speed of center of mass, so the speed of center of mass, what, let's call it v, what will be its value? So we know when this body is at the height h and it's not in motion, so initially, like in the beginning, it's just static there, it's not moving, so it has one form of energy called potential energy. So initially the body has potential energy, right? The value will be mgh. When it reaches down, so we know when it starts moving, this potential energy will transform in form of the potential energy value will start decreasing and it will start moving because some part is becoming its kinetic energy. And when it's in motion, a final value will be actually whatever the potential energy the body had, everything will become the kinetic energy. And finally, when it will come to halt, it will be zero, but just before that, the kinetic energy value will be this translational kinetic energy and this rotational kinetic energy. Again, using that solid cylinder, what is the moment of inertia? It is also half mr square. And again, taking v is equal to r omega value, we will substitute here. And since all this potential energy will convert and become the kinetic energy at the end, when the h will be 0 means it has reached here. All the potential energy has converted to kinetic energy. Means we can equate these two, potential energy and kinetic energy. And from this expression, we can write half mv square plus half, putting the value of I will be half mr square and omega will be v square by r square. Solving this, again r square cancelled, we'll be left with half mv square plus 1 by 4 mv square. This means 3 by 4 mv square. Now on this side we have mgh, so m cancelled, g, okay, g we have to keep as it is. Anyway, we have not been given any values, right? So we have to find out this v in terms of this g, h, it seems. So m cancel, we got cancelled, so gh will be 3 by 4 v square. Rearranging this to get v square, we'll 4 gh divided by 3. It implies that value of v will be, we'll take positive root of this, that means 2 under root gh by 3. So this will be the final velocity. Where is this? This, I think. Yeah. This is the correct answer. Okay, so these were till now the questions based on moment of inertia of flywheel experiment, and now we'll do questions based on now let's see what is the next experiment that we need to understand. So this experiment 4th, is about measuring surface tension of a liquid. So first let's start about understanding the theory of surface tension. So surface tension is the tension of surface film of a liquid caused by the attraction of particles in the surface layer by the bulk of the liquid, which tends to minimize surface area. So what happens in a liquid, like consider this is H2O molecule, consider this is some liquid, let's say that liquid is water and then this one molecule is H2O molecule, and we know there is cohesive force and adhesive force, right? We know these two types of forces, cohesive force and adhesive force. So we already have studied about different kinds of forces. So what is cohesive force? It's the force between similar kind of particles, right? Like here in the case of this liquid, all its molecules are exerting some force on each other and they are alike, so that force will be cohesive force. Then what is adhesive force? It is the force between particles which are different. Like here this is some beaker inside which this liquid is kept. So there will be a force acting between this liquid, the particles of this liquid and the particle of this beaker, whatever the material is. It doesn't matter here, but whatever the material is, there will be some force acting between this liquid particle and the particle constituting this material of the beaker. but they are different kind of molecules, different material, so the force that will be acting between them will come under adhesive force. So here uh, the force on one molecule because of the other molecules, they so this force, because of this force which is pulling this particular molecule in all direction, is the origin of this force called surface tension. And because of this is the tendency of a liquid to we know for any system, the system wants to be at the minimum energy, it wants to gain stability. That's why if we throw a ball from even if we throw a ball from down, it will go to a certain height and eventually come back. Why? Because the H wants to come to zero so that its potential energy will be less. So every system wants to come to the minimum energy level, the stability, the equilibrium. So here also the liquid, what it wants to do is it wants to uh, minimize its energy, and it is known that for a particular volume, for a particular value of volume, it can, if we think, it can take any shape, but different shape will have different area, right? If something is in form of cuboid, it will have different surface area. If something is in form of a cone, the surface area will be different. And then there is sphere, it has also different surface area for the same volume. But it's known that for a particular value of volume, again, like it can be in form of cuboid, it can be a form of cone or something else, or sphere. There are more things, but okay, just I'm mentioning these three. So for a particular volume, when it's take different kind of shape, the surface area of that shape is minimum when it is in the form of sphere. So we can calculate this and we can see that this is a true fact, and this is a fact, that when mass or volume of a body is in the form of sphere, its surface area is minimum, and the corresponding surface area energy of the material will be minimum. So as we said, that body tends to minimize surface area. Why? It tends to minimize surface area because it wants to minimize its energy, and this is what is called surface tension. Surface of liquid behaves like an elastic sheet because of this. And surface tension not only depends upon the force of attraction between the particles within the given liquid, but also on the forces of attraction of solid, liquid or gas in contact with it. So what the statement means is, surface tension not only depends upon this cohesive force, like this is the liquid particle and other particles of this liquid are also exerting force on this, but there is also the force acting between this material of the container and this liquid, that is also contributing to this surface tension, contributing to surface tension of the liquid. Surface tension in physics is defined as ratio of surface force to the length along which the force acts. So if we, it's given by force per unit length. Like if we imagine a drop of water, and this force actually acts tangentially, like it acts at a tangent. At every point the force is there, but it's acting tangentially. So surface tension acts tangent to the surface. So if we imagine this point, then, and if I draw it again, like the same tangent I am seeing from front, so at every point this tangent which is imaginary is just this is basically the force which is acting tangentially to the surface of this liquid. This is liquid drop we have taken. So the force, there will be particles exerting force perpendicular to this imaginary line. So that's why, it will be pulling this in all directions. So that's why we define this surface tension as force per unit length. So this is about the surface tension definition. Now the method that was discussed by the professor for determining the surface tension of a liquid, for measuring surface tension of liquid, the method is called capillary rise method. So we'll discuss the same method. So what is a capillary? If we have a hollow tube, like something like a straw, we all know what is a straw, right? We drink juice or water through it. So straw has like significant radius, but if we just imagine, capillary is a very thin straw. So its radius is very small, then we can call it a capillary. So when we have such tube called capillary and we insert it in a beaker like this as shown in the diagram, then we'll observe that even without us doing anything, when we'll insert the capillary, the liquid will rise inside the capillary. So the liquid was initially like this in the beaker. When we put this capillary, here I am showing it very wide, like in this diagram is also it's shown very wide just for ease of understanding, but otherwise capillary tube has very small radius. So when we'll insert this, the liquid will not stay here, liquid will rise, and depending on the nature of the liquid, we'll see either the shape will be like this, which is called concave. The water is still here, okay, and it has taken this shape as shown here. It has taken this shape, and this area is all air. This area is all air. Liquid is only till this portion. Let me show it properly. So it will be something like this. So all this will be the liquid. All this will be liquid, and here air will be there. So it depends on the liquid, because if you would have seen, if you mistakenly broke thermometer or something, we know mercury is there inside a thermometer, right? And if you will see, water, when it spills, it completely spills on floor or surface, but if you spill some mercury, you will see droplets, completely spherical droplets. So this surface tension again is a property of different of liquid, so its value is different for different liquid, and it depends on the nature of liquid. For water, the shape of this liquid rising will be like this, whereas if it's mercury, the shape of this liquid rising will be like this, which will be like here the water will be there. In this case, since we know surface tension acts tangentially, that means here it's acting in this direction. Surface tension, let's denote as S or T, whatever you want. Let's denote it using T. Here also it's tangentially it's acting. Here also tangentially it will act. Actually it's taken, the angle is taken. So this is called concave, this is called convex, and wait, this is the angle here. Anyways, I mean okay, let's not confuse here. Let me draw it properly also. What is important is this is for like water, and for mercury it will be, for mercury the liquid will rise like this. The liquid will rise like this. Anyway, so this is the capillary rise method, that when we'll insert a capillary in the liquid will rise, and depending on the nature of liquid, there will be particular shape of this end. And now to find out, I mean again we'll not go into derivation of the working formula, but what was the expression we'll start with. So the upward force due to surface tension on the liquid will be, there will be component to this, right? Or I can draw it again. Considering this, that the liquid that we took, sorry. Okay. So this whole setup, it is there. I'm just drawing this part. That it will rise something like this. It will make a sphere, half hemisphere actually. So if the radius of this capillary tube is r, so this is hemisphere, means this is r, this is r, this is r, and say the liquid was here, so this will be h. So, oh yeah, so this is the force acting tangentially, that is our surface tension. Let's use T here so that it will be different from everything. This force, it's acting at angle theta, right, from this container. So it will have, let's what we say, take its component. So here it will be T sine theta, here vertically will be T cos theta. It will, here also the same thing, T, its component T sine theta cos theta. We see this T sine theta, it will get cancelled, right, they are opposite direction. There is this T cos theta, everywhere it will be in same direction. So that force acting upward, so the force, upward force here due to surface tension, here we have upward force. This upward force is, since we know surface tension is force per unit length, right, so force will be surface tension times length. So here upward force due to surface tension means, due to surface tension the upward force will be this sine theta components are getting cancelled. We are only left with this component T cos theta. And the length is what? The length is, it's acting in all direction around the parameter of this. If I look from the top, then this is the capillary, right? This is the face of this capillary tube, and the liquid is also in the same shape. I mean, it's a circle. The liquid is also in this shape. So I mean, on all this perimeter tangentially, the what surface tension is acting. So basically the length at which it's acting is this whole parameter of this circle, this whole parameter, which is 2 pi r. So the length here is 2 pi r. So upward force is given by this, and then this particular volume of liquid that has risen above this amount of liquid in the beaker, that will exert a, otherwise it will keep on increasing, but there is a balancing force downwards. That's why this liquid is not rising after a particular height. So that downward force, that balancing downward force is due to gravitational the gravitational force acting on the mass of liquid. So downward force is due to gravitation, so we know that will be mgh, right? That force will be mgh. And how to know the mass? So mass we'll write in terms of density of liquid and then the volume, because we know mass is density times volume. Density we usually denote by rho, so yeah, and volume of the body. So density, let's say density of this liquid is rho, then we are left with volume. So volume of cylinder is what? volume of cylinder is pi r square, radius is r square, and h. Here the h is actually this, the height of this cylinder is this h plus this r. This h plus r is the height of the cylinder. But there is this, we'll subtract this amount of liquid because here it is air, right? So we'll subtract. This is hemisphere, so the formula will be 4 by 3 pi r cube. This is the volume of sphere divided by 2. So this upward force due to surface tension exerted on the liquid will be balanced by this downward force. So equating this and this, we'll get the working formula. We'll just come to this working formula, because derivation you can see in the video lecture. We'll be focusing on solving the problems. So just arriving at the working formula, the surface tension value will be density times radius divided by 2, and here it's h plus r by 3. There is acceleration due to gravity as well. So this is the working formula for this experiment. Okay, so in this experiment, what had to be done, you can again watch, you have already must have seen the video. Just to I'm just revising that here we'll take everything in this working formula. We can see G, density, is constant for a particular liquid when we want to find out. So G will be same, density will be same. What we can change is R. The H will be automatically done, we cannot do anything. But what we can change is the radius of this capillary tube. So for this experiment, we can take different capillary tube which have different radius, so that we can see what is the height for every capillary tube, and then we can take average of them to get a better precision in the final value. So that is about the procedure. Now again, moving on, trying to solve the problems for this concept. Just a minute. Yeah, we have time. So this is our first question. The question is, find the excess pressure between the inside and outside of a soap bubble of 20 mm diameter. So again, I would just like to repeat that these things we have already studied in class 11th, I think. But still, if you have forgotten or you have some doubt, the easy and standard text that I would suggest, because there is no text that has been suggested by professor for this particular course, but because we need to do these assignments, you need to revise and recall these concepts. So you can refer to NCERT class 11th physics book. There you will be able to see these quick formulas and you will be able to revise and recall. So here again, we don't want to derive these expressions, we will directly be using the final formula. So the same we will do, and what I want to tell you is that here the question is about finding excess pressure between the inside and outside. So excess pressure, how the question of excess pressure comes. So we know that when the liquid has risen, maybe concave or convex, whichever side, but it's not rising above, because there is some excess pressure on the other side that is acting on it, otherwise it will rise, or that mgh that we were talking about. So that is this called excess pressure, or in this direction, sorry, or for this there will be final this, yeah, there is a point of excess pressure so that the liquid is balanced. So here we have been soap bubble. So soap bubble is a layer of liquid. Inside also it contains air. For soap bubble I am telling, not liquid drop, it is not drop. This inside also it has air and outside also is air. So it has two surfaces. this on the surface it is that soap molecule, but outside it's air molecule, inside it's air molecule, so it has two surfaces. And we have directly this formula of excess pressure. So excess pressure, since it has two surfaces, it is given by 4T by R. Excess pressure P, the formula is 4T by R. T is the surface tension and R is the radius of this soap bubble. So, using this formula, the excess pressure for the soap bubble of 20 mm diameter, and okay, this is in millimeter, we'll change it into meter because we need to put it in SI unit. Surface tension we have given 0.15 Newton per meter, 0.15 Newton per meter, and radius is 20 mm. Oh sorry, this is diameter. Okay, so diameter is 20 mm, that means radius is 10 mm, and converting into meter means 10 to the power 3 meter. I think 10 times 10 to the power minus 3 meter will be the correct answer. So this will be 10 times 10 to the power minus 3. And the final, when we'll calculate, okay, I'm using calculator for this. Yeah, so 4 times 0.15 by 10. This will be 6. Wait, I just times. It will be 0.06 times, this will come to numerator, means 10 to the power 3. Okay. Removing this power, we will get 60 Newton per meter square. 60 Newton per meter square is the correct answer here. Now the next question. In previous problem, if it would be a water bubble, if instead it's a water bubble, that means a liquid drop. Water bubble of same radius and surface tension value is, now surface tension value is 0.08 Newton per meter, and radius is same. Last time we saw radius was 10 mm, and in meters it will be this. Then what would be the excess pressure? Now for liquid drop, inside, water bubble means inside also it's water, so the surface here it's air, on the surface it's water, inside also water, so it has only one surface. For this, the formula for excess pressure is, which we have been asked to calculate, the excess pressure is 2T by R. 2 times T is 0.08 divided by, this is the radius value, what will be the value? 16, then 0.16 divided by 10, and this will come here, so it will be 16 Newton per meter square. So answer will be this, 16 Newton per meter square. Now the next question, the work done in splitting a drop of water. Here we are dealing with water drop. Again, it has only one surface. So work done in splitting a drop of water of 1 mm radius. The radius is 1 millimeter. Again, everything is in CGS unit, so no need to convert, but we will convert it to centimeter because this is CGS. Right? CGS unit means centimeter, gram, second. This is what it means. So we'll convert it into centimeter, means 0.1 centimeter. So drop of water, this is there. It splits into 10 to the power 6 number of drops. So it later goes into, small. It splits into 10 to the power 6. This is the number of droplets, and of course the radius will be, I mean, this is lot number of droplets. They are all same actually, size is same, but number, I mean, they are smaller than the main one, right? Because it has split and changed into 10 to the power 6 number of droplets, whose radius we don't know, but we have been asked the work done in splitting a drop of water of 1 mm into 10 to the power 6 droplets. So what is the work done in splitting this? So work done will depend on the surface, depends on the surface tension, right? The energy. So the formula is, we know, we'll come to that later. First let's start with understanding, first let's calculate what is the radius of these small droplets. So what we have been given is the volume, since this whole big drop is splitting into these small droplets, that means whatever was the volume of these together will be same. So from this information we will calculate the radius of these small droplets. So volume of the big drop was 4 by 3 pi r cube. Let's call it, what should we call? Let's call it big drop. 4 by 3 pi r cube, radius is big drop. Here let's call it radius of big drop. Then the total, okay, radius of one of this small droplet will be 4 by 3 pi r radius of small droplet, and into 10 to the power 6, because there are total these many droplets. So comparing this volume, we'll get that volume of big droplet and its cube is like this. From this relation we can find out the volume of small droplet, which is the big droplet radius will be 10 to the power 6, and the radius of big drop is 0.1. okay, the cube of this divided by 10 to the power 6. Now we need to find out this radius, means we'll remove this cube. So radius of small drop is, we'll take cube root of this right hand side, so we'll get 0.1 divided by, we'll take the cube root of this, means the power will be this. So the value is actually, so 1 times, this will become 10 to the power minus 2 when it will come to numerator, and here is also 0.1. That means if I write it in this form, will be this centimeter. This is the radius of small droplet. Okay, we have found out the radius. Now we'll see what is the increase in surface area. We want to know the surface area because we know we started understanding the concept of surface tension by talking about the surface area, right? The liquid wants to minimize its surface area, and so that it can minimize its energy. So here it had some particular volume and it had some particular area. Now if the volume is same, but since it has split into many spherical droplets, so surface area has increased, and since surface area has increased means its energy has increased of the system. So we will find out what is the change in energy. That will be the work done actually. So first we'll find out what is the change in the surface area. So initial surface area formula for sphere is 2 pi r square. So the change in surface area will be, the final surface area will be 4 pi r square, radius of small droplets, and there are 10 to the power 6 number of droplets. So the total surface area will be this, minus the surface area of the big drop, 4 pi r square. The final we'll get 4 pi. This rs square is this 10 to the power minus 3 square of this times 10 to the power 6 minus 4 pi we have taken out common, so rb square 0.1 centimeter square, 0.1 square of this 4 pi. This will be 10 to the power minus 6 times 10 to the power 6. Okay, this is 0.01. So this will become, oh, minus 6 plus 6 means 0. 10 to the power 0 minus, if I write it in fraction form, that means 1 by 100. 10 to the power 0 means what? 1. Anything raised to the power 0, that means it's 1. So 1 minus 1 by 100. That means it's 100 minus 1, that is 99. 4 pi into 99 by 100. But our question is still not finished. We need to find out. So this I found out the change in surface area or the increase in surface area. Initially, because it was single big drop, there was some other surface area. Now it's split into smaller size but more number of droplets. So overall there is increase in surface area. We calculated what is that increase in surface area, which is this. It is also a centimeter square. This is the increase in surface area. Now to calculate the work done to increase this surface area, that will be surface tension times the area increased. Okay, I need add the slide here. Just a minute, we need a little space. Getting hang that, okay. I will add a slide. Yeah, I just needed the slide. So, okay, the work done or the increase in area will be the surface tension times the increase in area, or increase in area, increase in surface area, increase in surface area. So work done will be, the value we have been given, surface tension we have of water is given here. Surface tension of, where is my cursor? Okay, surface tension of water we have been given 80 dyne per centimeter. Using this 80 dyne per centimeter, increase in surface area is 4 pi times 99 by 100. 4 pi times 99 by 100. So the final expression when we calculate, let me calculate. It will be 80 times 4 times 99 times pi. I'll just take 3.14 and divided by 100. So what I'm getting from, I took pi as 3.14, then I'm getting it, if I'll take pi as just 3.14, then my calculation is giving me work done 994.752. Again, you need to take care of significant digit and all, but we need to get the values from here. So I think I can just, maybe I can just what we say, round off. I'll just round it off. Maybe the difference is, I think, because of taking the number of decimal digit of pi. So the best it matches is this D. So even if we round it off, it will become 995 and the unit will be erg this is the work done or the energy. So our answer will match. I think the difference is because of, I think it is because of the pi value that we have taken. So the answer best matches here. 995.25 erg should be the correct answer. Okay, so yeah. Or you can do it and confirm, and we may discuss it later. But I think it should be correct. So this is how we find out. I mean, just to summarize this particular problem, that we understood that surface tension comes into picture when liquid wants to minimize its surface area and to minimize its surface energy. And here, since one big drop is breaking into smaller radius but more number of droplets, so eventually the surface area is increasing, means the surface energy is increasing. And to increase that surface area, what is the work done or the energy we have to supply to do that splitting? That we'll calculate by surface tension times the change in surface area, which will be given by this formula here. And based on that, we calculated the work done to be 995 erg. Next question is, if soap bubble of different radii are in communication, I hope the recording, I heard some sound, yeah, what's going on here? Okay. So if soap bubbles of different radii are in communication with each other, so the question, soap bubbles of different radii, we have soap bubbles of different radii, one, let's call it bubble 1, and then there is another bubble 2. They have different radii. We have been given 4 options and we need to find out which one would be the correct option. These two soap bubbles are in communication with each other, means they are attached, something like this. So the situation is these two bubbles are attached, means this is the bubble 1 and this is the bubble 2. They are attached, and this is the some surface. It's when they are connected, there is some kind of shape the final one is taking. So this is the final shape of these when they are two connected. They are in communication with each other, means they are connecting, and the resultant shape is something like this. And the option is the air will flow from the larger bubble into smaller one until the two bubbles are of equal size, or the air will not flow from one to the other and the size of the bubble remain unchanged. C is air flows from smaller into larger one and larger bubble grows at the expense of the smaller one. D option is air flows from larger into smaller one. So this was bubble 1, this is not O2, this is bubble 2. This is bubble 2. This was bubble 1. Don't confuse. This was not O2. Bubble 2, smaller size, bubble 1, bigger size, because we have been told they are of different radius. And when they are in contact, this is the resultant. And we want to find out what will be the situation. The air, we know their air is outside because they are soap bubbles. That means outside, this is on the surface, it's the soap molecule, but outside we have air molecule, inside we have air molecule. The same is the case with this soap bubble also. They both are soap bubble. Just to keep it clear, these are soap bubbles. So inside outside air molecule is there. Okay, something happened.